Hello there. Today we are going to carry over from the last video where we are discussing temperature and heat, some confusing aspects of it. We want to be very clear about these concepts before we start to do problems in thermodynamics. Thermodynamics turns out to be a really confusing subject in physics, and that's partly because there are too many things that are just kind of arbitrarily thrown at you, and if you get the definitions right, I think the subject is not that complicated, and at least the beginning part. So let's see. So you probably recall that we talked about temperature in the last video, and so what's the temperature? Temperature is an intrinsic property, kind of just like mass is an intrinsic property, electric charge is an intrinsic property. Intrinsic. In the same vein, temperature is an intrinsic property. But what does it represent? It represents a state of the system that's in thermal equilibrium. And this is a pretty big deal to understand what it means. And so you can have a system which is thermally insulated from the rest of the world. And so system is what's inside here, inside these walls. And so this is the system here. And so this is insulating wall. So what you have here is, if you leave this for a long time, then all the internal processes, particles will hit each other, so they all kind of equilibrate to something that's reaches a time where it's have died out and not changing. So we'll say time goes to infinity, kind of we can loosely speak about it. It just time has elapsed, so whatever the processes here, they have actually it's not like molecules have stopped moving around. No, things are still happening, but overall the system is not changing. And this is the really very difficult thing to realize, that this will happen. So there are several time scales involved, and the comparatively speaking, one time is short time scale processes versus long time scale processes. So there is a comparison between the two processes, and short time continue to be there, but the long time thing have kind of come to some kind of steady situation. So this is one system. Another way you could look at it is so this is the inside of an oven. So say this is oven, and there is a filament, and this is, you're passing electricity through here, and this is heats up, and maybe you have something you're cooking, say chicken you're cooking. Okay. Well, inside the oven we'll have your basically you'll have infrared. So you'll have radiation, and maybe air here. So this is radiation here. Maybe filament, we can just leave it outside the system. And then there is this is another system. So you have two systems here. What happens is, and then there is some leak. So this will heat up, and so this loss of energy from this oven into this what you're cooking, and there will be temperature of the chicken will go up, and then this will give up radiation. So after some time, the energy that's coming in from here, let's put it like this, energy just coming in from here, energy that's leaving here, this say one balances the two, and over here the energy that's coming out of chicken into the oven and oven into the chicken, they are kind of balancing also. So this is 3 balancing 4, so 3 balancing 4 and 1 balancing 2. So situation inside there has reached a so-called steady state. Doesn't mean things are not changing, right? I mean, the heat is, the energy is being put in from outside, energy is leaving the oven to outside, but then energy from in oven, which is radiation plus air, this radiation is going in the chicken, and chicken is also radiating out. Chicken is also radiating out. But these processes are balanced. These processes are balanced. They're happening. And so what we can say that because of this balance of processes here, the temperature in the oven is equal to temperature in chicken. So temperature in the oven equals to the chicken. Okay? So this is a thermal equilibrium also. But this is a different kind of thermal equilibrium as this, where you kind of have a system where it's just steady. Here we have a comparative system. Okay, so we have temperature is an indicator of a property I can assign to something in thermal equilibrium. Okay, and I want to make sure temperature is not heat. Okay, so what is heat? Well, heat is another very confusing property, right? So heat is actually not a property of anything. Not a property of anything. Let me come as a surprise to you. Use the word heat and heating and all those things, right? But we don't say an oven has heat. No. So heat has to do with energy. First of all, heat is energy. Heat is energy in flow. So energy that's moving from a system to another system in flow from one body at one temperature to another body at another temperature. So this is what heat is. So you can use heat to account for energy balance, but you can't really have heat, an object having heat. So here is a let's look at this again. So say I have just oven, and here is a filament. So I will pass electricity, and this filament will heat up. So this will have some temperature of the filament, and then rest of the oven is going to radiate out energy, and it's going to distribute in the rest of the oven. And then there are walls. Let's see, these walls are walls are completely ideal. Let's see, ideal insulation. So like nothing is escaping. So what do you think is going to happen? I pass in energy. There's some registers here, so it heats up. So you can think of this being one system A, and this thing being system B, rest of this. So this situation, we would say energy from system A is going into system B. Why? Because system A is at a temperature TA and system B is a temperature TB, not equal to TA. So this is initially heating. Okay. And so maybe initially inside of this here, the temperature was say 25 degrees Celsius, and this thing is say 500 degrees Celsius, this filament. So you are going to have difference, and so because of that, naturally the natural process is to go from high temperature to low temperature. You can violate the natural process by, in a refrigerator, right? If you can arrange a system in which you can take energy from lower temperature to higher temperature, like from inside the refrigerator to outside, but that's not natural. Okay, so naturally heat will flow, or energy which we say through the heat form flows from the high temperature to low temperature. So temperature, and so temperature of this thing will go up. So this will go up, and these walls will heat up, right? These walls will heat up, this inside wall, and they will radiate heat also, radiation also. They will radiate out energy as well, and those radiations will go into the heating filaments as well. So you will say initially A is giving heat into B, and very little from the B is coming into A, and then equilibrium will reach when A is giving heat, the energy to B, and B is also this same radiation. Let's call this radiation energy. Radiation going into that and radiation going into that, and they are balanced. Then we have reached equilibrium, and you have to at that point the filament will have to, this energy will be shut off. This, because this ideal, we don't need any more energy, so this oven can remain at some temperature that at which this balance takes place. So this TA equals to TB, and this is TA is greater than TB. So this is how heat, the energy transfer from one body to another body takes place through the way of heat. Okay, now this is too abstract and doesn't lend itself to actually quantitative calculation. The thing that lends itself is when we look at energy picture in a more broader way. Okay, and that's what I'm going to do, and that's where the first law of thermodynamics comes in. All right, and it provides a mechanism for actually thinking about these things in a more quantitative way. Okay, so let's look at how we can quantify some of these things. How do we quantify? How do you quantify this? So we have again consider oven again, and we have some heating elements. So some current goes in, and then radiation comes out of here, and maybe there is a aluminum bar here, bar at temperature T0, initially at temperature T0, maybe T0 degrees Celsius. Okay, and when this radiation gets absorbed by the molecules here, you are going to heat this up, and then it will also radiate away. And say this oven is set to have a final temperature T final. And so this, if you look at this bar as a system, so this is my system. It will be in thermal equilibrium with the oven at TF. So it went from T0 degrees Celsius, so TF degrees Celsius, and the bar, this aluminum bar volume didn't change much. So we say like a dV equal to 0. So if it changed, then some of the energy would go into there's a stress inside the bar. So if you look at the bar, we've talked about this is a bar, and then you can see inside molecules are attracting, right? Say this molecule, if it gets expanded, then these molecules will be separated further, and so there will be energy that will be stored as a result of deformation of the bar. But we are saying the bar is not deformed at all. So all the change in energy of the bar, delta E change in energy of bar, this is change in energy of bar from initial to final, is all due to change in temperature. All due to temperature change at constant volume. So this kind of thing, you can actually take aluminum, you can say how much energy it took to, so if you take an aluminum, so this will be material and maybe amount of material, and you can say I went from T0 to TF, how much energy it took to get there. So amount, say for amount we can just say mole or gram, so let's say mass. So if you did this, you'll find that this is actually proportional to these two things, proportional to amount you had of aluminum and you had amount of temperature that you had to go through. And so this is if to make it equal, delta E is actually some constant times mass times TF minus TI. Let's call it TI instead of T0. And this C is called, little c actually, called specific heat. So in this scenario, if I did this scenario with not aluminum, say if I did with copper, and you did the same kind of stuff, you would find that C for that is different. This also, again, delta E is C for copper, amount of mass I took, TF minus TI. So this will be different than that, and that will be reflected into the specific heat for that material. So each material, I can do an experiment like this, and I can quantify how much energy it took to change the temperature. And that's this thing I needed to change temperature is called amount of heat. Heat was needed. So this is, it didn't go anywhere. It's just to cause the change in the temperature of the material under constant volume. I was able to, I need that much. And so that is one way to look at heat. So delta E equals delta E at constant volume is the amount of heat. So if you change energy at constant volume of these materials, like a bar or a gas or a liquid, then you can say that if there are other ways energy can like a potential energy can change, then this won't be the case. So everything else have to be fixed except the temperature is being varied, okay? And this is this will take place. So in this situation, we have a formula for Q. Q is the symbol used for heat usually, and you can see Q is not E, but it related to delta E. So Q can be MC. We'll say constant volume by putting and this is going to be later, constant volume, and we can say delta T I needed to change. So this is, in this experiment you can have the heat. Now there are other experiments in which you can measure heat that you'll be involved some other way. So let me look at other experiment. Now let's look at an experiment where we are maybe we have water at say 100 degrees Celsius, and let's say 0 degrees Celsius. We have water degrees Celsius, and we put in a very cold place. The outside is just a little bit less than 0 degrees Celsius, almost like that, maybe minus 0.01 degrees Celsius, so that the energy can escape outside. And then, so this was at t equal to 0, time equal to 0. Later on, this will all freeze up. It becomes solid ice, and still temperature is 0 degrees Celsius. So this is Ti was 0 degrees Celsius, and this is Tf was 0 degrees Celsius. So now I didn't change any temperature. There is a little volume change. There is a small amount of volume change, right? There's a small amount of volume change, which I'm going to ignore. So the question is, how much energy did I take out total? Okay, delta E. So delta E, this delta E is actually if you say this is proportional to n delta T. If you say this is equal to NCV delta T, then it's going to give you 0, right? Because this is T final minus T initial equal to 0. So this is not what's going on here. What's going on here is water used to be in the liquid phase, and now it's become solid phase. So what's happened is, this is initial state and this is the final state. The temperature is same. So initial state was Ti was 0 and liquid. final state, T final is 0 degrees Celsius, but this is solid phase. Now, solid and liquid, there is a difference in binding, and the movement of the molecules. Okay, so this one, if this has some energy E initial and this energy final, it actually depends on only, you can quantify by how much material you got. So E and delta E is proportional to just the mass of the material. And you have water or you have some other liquid, proportionally constant will be proportional to that. So delta E will be proportional to m times some other constant. Okay, and so this will be maybe letter L is used. L is H2O, or freezing or melting. So the types of process that H2O is going through in terms of phase change. So this is L is a constant, and it is associated with the process and the material that I'm looking at. Just like C is process and the material that we're looking at. So this C was another kind of constant, which was associated with the temperature change and amount of heat. And over here, this also amount of heat, but the L is associated with change in phase, not temperature change. And this L constant is called, over here you can say specific heat of maybe freezing. So if you can imagine, if I had a liquid and then I heat it, I put some energy in, and this became steam, the whole thing in steam. So this delta E, this initial temperature is say 100 degrees Celsius, and final temperature is 100 degrees Celsius, but they're not the same phase. So this delta E will be amount of material I convert into steam, L of say this is H2O, this will be boiling, and so this thing we will call it, this L will be a specific heat of evaporation. And if I condense it, you can call it condensation. It's going to be the same number. So this is another formula for, you can say, this is the Q for this process. This is the Q for this process. So this is the Q for that process. This is the Q for that process. So now we have a formula for Q, like 3 different formulas here. So we have 3 different formulas for Q. So there's a Q equals to M CV delta T, and then we have a Q equals to M L freezing, and the Q L evaporation. So you can see it depends on where we are using, what process we're looking at. So this is the formula for Q. Now, how does it work with First Law of Thermodynamics? First Law of Thermodynamics. We are going to use First Law of Thermodynamics in near future. First Law of Thermodynamics says that if you have a system at Ti, and it's got some energy EI, and maybe you're exchanging heat, maybe you are you expanded the system, so meaning you maybe your pressure was lowered, change the pressure, or whatever situation is, you are doing something, and then the final, you have a final state, and it is energies, and the final state is EF. So you've gone from here to there, and you did something in between. So what can you do? What kinds of things that will change this energy? Well, one would be the heat type. So the delta E will consist of some energy that are done through the mechanism of different temperature, okay? And then the other kinds way energy could be done is an example will be like, suppose I had a gas here as my system, and I had a piston and a push on it. So there's a force I apply, and then the piston kind of moves over here. So the gas is now less volume. So this is inside there, gas energy will change by P dV, by that formula, or F dx turns out to be P dV. This is the stress inside the gas, and this is the change in the volume, okay? This is strain, this is stress. So this one thing can happen. And say another thing will be, say I have a all these magnets are pointed down, for instance, and I put that in a magnetic field like that. These magnets flip, so they will lose energy as a result of that. So this will be like H dm. This is another way energy can change. So these are not heat type of energy, because this didn't happen because of difference in temperature, but this happened because some other property changed, right? So all of that we are call it work. All of this kind of things is mechanism by which energy can change, is called work. Yet another way energy can change is if the chemical composition changes, right? Inside, say I have a chemical reaction going on, then it can produce some heat, and it can produce some more energy. You might call it chemical energy. And so there will be energy associated with change in chemical position, plus delta, you can say delta E due to change in chemical. You may also get energy change because there is nuclear reaction going on, which nuclear reaction you can address that the same way as chemical. You can say number of particles, types of particles that are different. So all of this can be caught by saying energy associated with types and number of particles in the system. So their composition of particles changed, right? So so there are these three mechanisms by which energy, you can account for energy. Another way is say if the system is on this table and this is the center of mass, system goes over here. So this is like center of mass change. So this another form is another way energy can change is I've got a gravity potential energy because I changed the center of mass. Well, another would be this center of mass has a velocity 0, and I hit it, and center of mass is going now with velocity VCM. Well, that will be kinetic energy of center of mass. Change in potential energy, change in kinetic energy center of mass. Another would be maybe I hit it here, and over here it kind of rotates. So there will be maybe kinetic energy of rotation. Now a rotation, overall rotation, right? Now these are, usually we don't include them when we talk about thermodynamics. These are kind of external. They're called external, while these guys will be called internal. This will be called internal energy change. I mean these two, these 1, 2, 3, this will be called internal energy change. Let me clear that up. Just to clear up the slide, so we have energy changed from some initial time to some final time, and some came from heat, some from work, some from change of number and types of particles, and then some from having to this like a change in cm, kinetic energy, and things like that, right? So this part is what we call change in internal energy. Internal energy. So this is, I'm talking about change. We're not talking about Q cannot be an energy. It's can be related to change in energy, and this is the external one. In thermodynamics, we just deal with this guy. So we say we are going to look at system where this is 0. So we just, this will be called delta E internal, and sometimes you use a letter U for this internal, and you don't even say internal. So we say U, you don't see U, there has to be change in internal energy. If I use this common symbol U for internal energy, it will be some heat, some work, plus delta E, number and types of particles that make up my system, right? Now it turns out that we go even further than that. If we don't change this, like no chemical reaction, if this will be 0 if no chemical reaction, no nuclear reaction, no diffusion of particles in and out of system, in and out of system. So if this is 0, then we just have these two to work with, and when we have just these two to work with, we call if delta U is just Q plus W, if that's all we got, then we are working with, this means I'm working with what is called closed system. These systems are closed systems, and we don't have to worry about taking into account changing particle things. So we are going to clarify in the coming days, how to take care of this, and we probably mostly we're going to work with, we will work with gases, and not, magnetism and things like that. So we're going to mostly work with gases, and very simple gases, including ideal gas. This we already learned a little bit in this lecture, but we are going to put all this together after we look at this thermodynamic work, how to find work in various processes that involve gas, a given amount of gas, and we expand it and continue to it. We do certain things to the gas, and we'll talk about the work in the next video, and we do some problems, because a lot of the questions that come up in thermodynamics actually ask you to find work done in a given process. And so we're gonna do a video on the work involving gases. Okay, so we're gonna look at various situations in which how to come up with a formula for finding work. Okay, if you like this kind of video, please hit the like button, and subscribe to this channel. Okay, and check out also my website of physics bootcamp.org. Okay, thank you, and we'll see you in another video. Bye.